As we know that the eigenvalue problem is if an operator operate on this state vector, we get the same state vector with a constant a. This is called eigenvalue problem. This is called eigenvalue problem. Here a is the eigenvalue, psi is the eigenvector, and a is the operator. Now we will calculate the momentum operator in quantum mechanics. Suppose a free particle moving in x direction. If a particle is moving, then there is a wave associated with that particle. So the wave function or the wave associated with this particle, this moving particle, with this particle is, which we already discussed, is given by psi of x over t. The wave function is a function of both position and time, and is given by a e raised to power iota over h bar p of x into x minus et. This is equation number 1. Here a is the amplitude of the wave function, px is the momentum along x direction, e is the energy of the particle which is moving in x direction. Now differentiating equation 1 with respect to x position, we have, if we differentiate this wave function psi of x over t with respect to position x, we get a as a constant, so we can keep it outside of the differential operator, and we have partial by partial x of e raised to power iota over h bar p of x into x minus et. If we apply this differential operator partial by partial x on this exponential factor, we get iota over h bar p of x, and then again the same exponential factor which is iota over h bar p of x into x minus et. This can be written as iota over h bar and p of x, and then we have a e raised to power iota over h bar p of x into x minus et. Now this is the wave function given by equation number 1. So instead of this, I will put iota over h bar p of x. I will put the same wave function psi of x over t. So partial psi of x over t over partial x is equal to this one. Now bringing this factor to the left hand side, we have h bar over iota partial psi of x over t over partial x is equal to p of x psi of x over t. Now multiply and divide the left hand side by iota, we get minus iota h bar partial psi of x over t over partial x is equal to p of x psi of x over t. Now this is very important equation. This is an eigenvalue problem. It is similar to this one. Here we have the operator, which is this one. This is the operator which operate on this wave function on this state vector, give the same state vector like this with a constant p of x. So here p of x is an eigenvalue, like a is an eigenvalue, so here p of x is an eigenvalue. Similarly, psi of x over t is an eigenvector. And minus iota h bar partial by partial x is the operator. Now is the operator. Now this operator operate on this state vector psi of x over t. We get the same state vector with a constant, and the constant is the component of momentum along x direction. So it means that the momentum operator in x direction is p of x. For operator we use a cap above it, is minus iota h bar partial by partial x. This is momentum operator along x direction. Similarly, the momentum operator along y direction is p of y. If we do the same calculation, we get minus iota h bar partial by partial y. And the momentum operator along z direction is pz, which is minus iota h bar partial by partial z. And three-dimensional K form, and three-dimensional form the momentum operator is which I will represent by this p, and is minus iota h bar, this del vector. Here this del vector is given by partial by partial x into I plus partial by partial y into j plus partial by partial z into k. Here I, j and k are the unit vector along x, y and z direction respectively. So this is all about momentum operator in quantum mechanics. In the next video we will derive the kinetic energy operator, or the operator for kinetic energy. Thank you.